Hello. So this is exam 4. The first section is chemical reactions. You're going to start with calcium added to water. So just starting off with what it says we have added together, we have calcium. And when an element is on its own, we go based off the elements on the table. Calcium is a metal, so it's a solid at room temperature. And we have water, which is H2O, and it's a liquid. So another way to look at this equation is to rewrite water as HOH. When it looks like that, it kind of looks like we're doing a single replacement reaction. We have a single thing on its own here, and we have something in a pair over here. So we're going to take this hydrogen and switch it with calcium. So on this side, calcium is going to be combined with the hydroxide, the OH. When we have calcium, calcium's a 2+ on its own, and hydroxide is OH1-. So we need 2 OHs to make it complete. And then hydrogen, when it's on its own, is diatomic. So we don't just put H, we put H2. And calcium hydroxide is a strong base, so it's aqueous in water, and the hydrogen is gas at room temp. This type of reaction, I kind of spoiled it, we have one thing over here, and we have 2 things over here, which means it's a single replacement. Metallic aluminum reacts with fluorine gas. Aluminum and fluorine. Fluorine is diatomic, so we're going to put F2. And it said that it's fluorine gas, so that's G. And aluminum is a metal, it's a solid at room temp. You have 2 individual things being combined together. That's going to be a combination of the 2. So this is a combination reaction. So we're going to have Al and F. Al has a 3+ charge and fluorine has a 1- charge. So when we put these together, when we do our crisscross, it's going to be AlF3. And we assume this is an air, so this is solid. Hexane gas, which is C6H14, burns in oxygen. So it's a gas plus O2 gas. Anytime you see an organic compound, meaning it has carbon, a combination of hydrogen and sometimes oxygen, and then it's added to oxygen is added, it's a combustion reaction. Every single time it is combustion. And if it's combustion, then your products are always carbon dioxide and water. I'm going to leave a little bit of space for balancing. I haven't done any balancing, mind you. I've just written out every equation. Don't forget that H2O is a gas in combustion. I'm going to go back and balance after this. Barium oxide, that is BaO. Barium has a 2+ charge, and oxygen has a 2- charge, so it's just BaO. And that is a solid, is added to water. Once again, we're going to think of water as... So when barium oxide is added to water, this is a very special type of combination reaction. If we go over to your lecture outline, this goes under metal oxide plus water becomes a base. So in this case, we have the metal oxide of barium oxide, and it's added to water. So when we combine these together, we're going to get barium hydroxide. And that we have two hydroxides because barium has a 2+ charge. And this is a strong base, making it aqueous. The final one we have is lithium carbonate is heated. So we have Li2CO3. And this is a solid because it's not in water. And when this is heated, it's going to decompose into, if we look at our decompositions, a carbonate decomposes kind of the reverse of what we see here, where a metal oxide plus a non-metal becomes a compound. This, we see calcium oxide and carbon dioxide added together to become this solid. But over here, we see the carbonate decompose into the metal oxide and carbon dioxide. So carbonates become oxide and CO2, hydroxides become oxide and H2O, and you're not required to know sulfites. So since we have CO3, this is going to become LiO, so it's Li2O, because this is a 1+ charge and oxygen has a 2- charge. So when you crisscross, you need 2 lithiums to balance it out. And once again, this is an air, so this is solid plus carbon dioxide gas. And this is a decomposition reaction. So let's go back and balance. In our first reaction here, we have on our reactant side and our product side, we have CaO and H. So I have 1 calcium, 1 hydroxide, 1 oxygen. Oh, sorry, I went to put calcium hydroxide. That's how we'll look at it, like this. And H, so we have a calcium, 1 hydroxide, and 1 H. And on this side, we have 1 calcium, 2 hydroxides, and 2 H's. So the easiest thing to do is just to double this height, the water, which changes this to a 2, and this to a 2, making this one balanced. In our second one, we have a little bit of a tricky situation here. We have 2 fluorines here, but we have 3 fluorines here. So let's make our little table. We've got Al and F. On this side, we've got 1 aluminum, and this side we got 1, this side we have 2, and this side we have 3. So the easiest thing we can do is take the 2 numbers and put them on opposite sides. So on this side, we're going to put a 2, and this side, we're going to put a 3. This updates the fluorine to 6 on both sides. However, now I have 2 aluminums on the product side, so I'm going to need to double the aluminum on this side to make them both 2. And that one is now balanced. For our third one, we have the combustion reaction, which is unfortunately one of the more difficult ones to do. So I always do CHO for these. We're going to have our reactants and our products. I have 6 14 and 2. And on this side, I have 1, 2, and 3. Something to note is anytime you are given a combustion reaction and the amount of carbons is even, you're going to eventually have to double the whole thing. This whole thing you're going to have to double eventually. So what you can do is just skip while you're ahead and just double everything to start and then figure the rest out, because at the end you're gonna have to double everything anyways. So this becomes 2, 4, and 6. This side we've now got 12, 28, and 4. To get this to 12, I'm gonna have to just multiply the 2 by 6, which gets me to 12. Now I've got 12. That also is going to update this oxygen. So I've got the 12 times 2, which is 24, plus the 2 that I've got over here. Giving us 26 oxygens on this side. So now we're going to do those hydrogens. So currently I have a total of 4 and I have 28 on this side. So I'm just going to look here, and to get 2, ignoring this, if the 2 that quantity that I have, 2 to 28, I need to multiply by 14. So I'm going to just change this to 14. And if you look, that's the amount of hydrogens I have. So I know that that's the exact amount of number I'm going to need. So now I have 28 on this side, got 28 on that side. All I have left is to do the oxygens. So I've got 26 here. I need a total of 26 on the other side as well. Something times 2 is going to get me 26. The number is 13. So this is your completed reaction. Like I said, it's, in terms of balancing, probably the one that takes the longest amount of time, because it's the only one that's going to have long numbers like this. I will say, typically, when it's doubled, it follows the pattern of this is going to be the same number of hydrogens, and this is going to be double the amount of carbons when it's doubled. It almost always follows that pattern, and then you just kind of have to figure out how many oxygens there are, based to like balancing it out. Next one we have is barium oxide plus water. So to balance this one, we've got barium. This one, I can't do the hydroxide trick because we have oxygen on this side already. So I have barium. I'm going to do hydrogen first and then oxygen, reactants, and products. So I've got 1, I've got 2 and 2 on this side. I've got 1, 2, and 2. Hey, it's balanced. I don't have to do anything. It's my favorite kind. On the bottom, gonna do the same kind of thing. I've got lithium, carbon, and oxygen on the. Then I have reactants and products. Lithium, I've got 2. Carbon, I've got 1. Oxygen, I've got 3. 2, 1, and 3. Hey, it's balanced. I don't have to do anything. Life is easy breezy. Okay, so for our next section, we have the net ionics. All of these are going to be double replacement reactions, double and single replacement reactions. So for the first one, it reads that solutions of ammonium acetate and calcium sulfate are mixed. I'm going to start by figuring out our formulas. So ammonium acetate, that's NH4C2H3O2, because both of these have a one charge. This one's +1, and this one's -1, so they balance evenly. We've got calcium, which has a 2+, and this is SO4, which got 2-. So when we get to write it, since it's a 2+ and a 2-, that's just calcium, SO4, calcium sulfate. So when we put this together, we have NH4 you have NH4C2H3O2, and that is aqueous because ammonium and acetate are always aqueous in water. And it also hints, it says solutions of ammonium acetate and calcium sulfate. So even though calcium sulfate, everything in your soul is telling you that it is insoluble in water because it is insoluble in water. It says solutions, we're going to write it as a solution. So we have calcium sulfate aqueous, even though my whole body tells me not to. Now we're going to write our products. So NH4 is going to now go with the sulfate, and acetate is now going to go with calcium. So when we rewrite this, we have calcium acetate plus ammonium sulfate. So we're going to have 2 ammoniums, and then we have SO4. Now this, we need to figure out our states, and that determines whether or not we have a reaction. Calcium acetate. We said that that acetate is always aqueous, so that means this is aqueous. We also said ammonium is always aqueous, so this is also aqueous. If my products are 2 aqueous ionic solutions, do I have a reaction? No. This is no reaction. That means my total ionic is no reaction. My net ionic is no reaction. I don't have to do anything. If you wanted to be safe and special, you could do the total ionic. Let's do the total ionic. So I've got NH. Oh, wait, no. That means I have to balance this. Okay, let's balance this. I'm going to do this quick and easy because the whole point is that this doesn't happen, and so it's okay. All you need to do is slap a 2 here, and that's it. Okay, so I've got 2NH4+. These are always aqueous. Plus, that 2 connects to that acetate as well. So I've got 2C2H3O2, 1- aqueous. Plus, calcium, 2+, aqueous. Guess what? Plus SO4, 2- aqueous. And this becomes calcium, 2+, aqueous, plus 2C2H3O, 2- aqueous, plus NH4, and that's 2 of them, and this is a 1+ aqueous. And then, of course, SO4, 2- aqueous. Oh, that was really bad. Aqueous. So when you do our next part, where you cancel out everything that doesn't match up, or that does match up, then you cancel out the whole thing, and then you still get no reaction at the end. So if you want to, you can do this whole part. And then at the end, you have nothing that stays on both sides, so your net is literally nothing. There's no net. Everything falls through the net. There's no net. It's catching nothing. I'm going to be so for real with you guys. They're not going to make life easy on you. They're not going to give you 2 no reactions. Both of these would result in no reaction. So I'm going to do something a little silly, and we're going to change this up, swap some things around for there to be a reaction. So This is no longer ammonium acetate, and this is no longer calcium sulfate. We're going to pretend that we started with the products instead. So over here, we've got ammonium sulfate and calcium acetate. And over on this one, because spoiler alert, it's gonna do the same thing. And they don't make it that easy. Why would they ever make it that easy for you? So we're gonna start with potassium sulfate and barium hydroxide. So going back to the first one, since we're doing it again because I hate myself, we have ammonium sulfate, which is going to be, as we determined before, NH4 SO4, pause for dog. Ammonium sulfate is aqueous because ammonia is always soluble. This is added to a solution of calcium acetate. Also aqueous because acetate is always soluble. And it tells us they are solutions. So when these two are mixed, we're going to take the NH4 and put it with the acetate. And then we're going to take calcium and put it with the sulfate. So we have NH4C2H3O2 aqueous, because we said both of those are always aqueous, plus calcium sulfate. As we talked about before, calcium sulfate is insoluble in water. So, because of this, we've got a reaction. Kind of like what we talked about before. To balance this, I just slap a 2 here and call it a day. Since this is aqueous, when we do our total net ionic, we're going to split these two. So we've got 2 NH4 pluses, aqueous. We got 1 SO4 2 minus, that is aqueous. Then we got 1 calcium, charge is 2 plus, which is aqueous. And then 2 C2H3O2 minus, aqueous. This becomes 2 NH4 plus, aqueous, plus 2 C2H3O2 minus, aqueous, plus calcium sulfate. Because this is solid, so it's not going to split into the two, it's just going to stay as it is. So now we're going to look at both sides and figure out what's the same on both sides. We've got 2 ammonias on each side. I've got 2 acetates on each side. Everything else will carry down. So we've got SO4 2 minus, aqueous, plus calcium 2 plus, aqueous. And that becomes calcium sulfate, solid. And that is the first one. Number 2, we've got a combination of barium hydroxide. We've got BaOH2, because this is a 2 plus and this is a 1 minus. So when we crisscross that, this one's going to get a 2 and this one's going to get an invisible 1. Over here, we've got potassium and sulfate. So when we crisscross the 2 minus and the 1 plus, we're going to get a 2 with potassium, giving us K2SO4. So when we write out our molecular, we have barium hydroxide, which is a strong base, so it's aqueous, plus potassium sulfate, also aqueous. when we combine these two, we have, not combine, sorry, when these do their reaction, barium is going to go with sulfate and the hydroxide will go with potassium. So we have potassium hydroxide, which is a strong base, and this is group 1, so it's always aqueous, which is part of why it's a strong base. And that's aqueous. Plus, we have barium with sulfate, so that's BaSO4, and for the same reason that calcium sulfate is insoluble, barium sulfate is insoluble. It's one of the three guys, wise guys, or some people remember Castro Bear. Either way, this is insoluble. So this is our driving force. This is the reason we have a reaction. So when we put this whole thing out, anything that is insoluble is going to stay together. Only thing that follows that is barium sulfate. Everything else is going to get split up into their ions. So we have barium. Oh, I didn't balance. So, got 2 potassiums here, 2 hydroxides. Slap a 2, call it a day. So I have barium 2 plus aqueous plus 2 hydroxides because of this little 2 down here. That's minus aqueous plus 2K plus aqueous plus SO4 2 minus aqueous becomes 2 potassiums aqueous plus 2 hydroxides aqueous plus barium sulfate because it is solid. So we're going to look at what is the same on both sides and cancel them out. Potassium is the same on both sides. Hydroxide is the same on both sides. Those are our spectator ions. Everything else is going to drop down. So we've got barium 2 plus aqueous plus SO4 2 minus aqueous, and that becomes barium SO4 solid. Now we have aluminum is added to a nitric acid solution. Aluminum, it's just aluminum, so that's Al solid, plus we have nitric acid, HNO3 aqueous from the activity series. I remember 3, 5, 4. So these 3 can swap with liquid water or react with liquid water. These 5 can react with gas water. Everything here, this doesn't seem right. Do they not have, I think they didn't put one. Anyways, these are, why did they not put it? Doesn't matter. These can react with acids and everything below cannot. So that is our little setup we've got going on. Ew, math. Okay. So aluminum plus nitric acid. So let's go back actually, because I forgot what I was doing. Aluminum can react with the gases, the gas water, meaning it can react with acids. So when we go back, since it can do that, we allow this reaction to happen. So this aluminum is going to pair with the nitrate. So we have aluminum nitrate, and it's aqueous, and it's going to free the hydrogen gas. This would bubble, basically. So we have, to balance this, unfortunately, I've got a 2 here and I've got a 3 here. The only way to make anything happen is to make 6 total. So we're gonna have to put a 2 here and a 3 here, meaning we're gonna have 6 of these, and we need 2 of these. So that's that. Okay. So for the total ionic, side note, if you still need to do the products and reactants thing on the side, absolutely fine. I probably needed to do that my entire way through probably 111. Anywho, for our total, because this is solid, we're going to keep it solid. So we've got 2Al solid plus, this is a strong acid, not a weak acid. So we're going to take this and ionize it. So we've got 6H plus 6NO3 minus aqueous. This is going to become, we have 2 aluminum. There are 3 plus ions plus, we got 3 nitrates. Oh, no, we don't. We have 6 because we have this number times this number. And those are aqueous. Plus, we have 3 H2 gases. It's not aqueous, I don't split it up. We're going to take what's the same on both sides. Nitrate and nitrate are the only thing that's the same. The 6 hydrogens became the hydrogen gas, and the aluminum became ions. So the only thing we're crossing out is nitrate. That's the only spectator ion. So our final net ionic is 2 aluminum solid plus 6 hydrogen ions becomes 2 aluminum ions plus 3 H2 gases. Okay. For D, we have solutions of sodium sulfite, so that's NaSO3, Na2SO3, and nitric acid. So we have HNO3. They are mixed. So we have, once again, Na2SO3. That is aqueous because it's a solution. And we have HNO3, which is aqueous because it's a solution and because it's a strong acid. When we combine these two, we're going to swap out dance partners. So sodium's going to go with nitrate and hydrogen's going to go with sulfite, giving us sodium nitrate. Almost wrote out nitrate. And that is always aqueous, plus sulfurous acid, H2SO3, aqueous. You're going to look at this and go, there's no reaction, that's aqueous. Everything's aqueous. You are wrong. This is not a strong acid. This is a weak acid. Weak acids do not ionize when you get to your total net. That's why we did solution inventory. That's why we remind ourselves that this stays mostly as itself, even though it's dissolved. It's a weak electrolyte. If everything was strong electrolytes, then we'd have no reaction.
I'm not quite sure how to help you with that.
That's crazy work. Anyways, but because we have a weak electrolyte, as long as one weak electrolyte or one non-electrolyte is produced, then we have a reaction. This is a weak electrolyte, therefore we have a reaction. So this is going to, as a reminder, I'm going to circle it. We are not going to ionize that. So we have 2, I forgot to balance again. Okay. Ew, okay. Double this, and double that, and that's that. Right? Yeah, okay. So we have 2 Na plus sulfite, and that is aqueous because it says so. 2H plus aqueous because the whole thing's aqueous. 2 nitrates, aqueous because the whole thing's aqueous. And then we got 2 sodiums that are aqueous. two nitrates that are aqueous. Got two H. I circled it. So we have H2SO3 aqueous, and that's going to stay as it is. Now we're going to do our crossouts. Sodium, same on both sides. NO3, same on both sides. Only thing that stays, you got the two things that make sulfurous acid. So we have SO3, 2 minus, aqueous plus 2H plus, aqueous becomes H2SO3 aqueous. Okay, before we do anything else, let's balance this equation. Ew. Sorry, it's ugly. Okay. So we have Ag, H, N, and O, Ag, H, N, and O. So I've got 1 silver, 1 hydrogen, 1 nitrogen, 3 oxygens. And then I've got 1, 2, 2, and 5. That's disgusting. First things first, I gotta double my hydrogens on this side. That is gonna get me 2, 2, and 6. Also, this is supposed to say copper. This isn't supposed to say copper. This is supposed to be silver. And they intended this to not be nitrogen monoxide, but nitrogen dioxide. Okay, so I was like, this seems like low-key impossible. Okay, it's balanced. All I needed was a 2 here, and then the rest is fine. So, just fill in our 1s. How many grams of silver are needed to produce 168.26 moles of silver nitrate? So, we are starting with moles of silver nitrate. And we need to get to grams of silver. I can go from moles of silver nitrate to moles of silver pretty easily using the molar mass, or not molar mass, the molar ratio, because I have the equation which gives us all of our molar ratios. We've got the stoichiometry going, and we'll go from moles of silver to grams of silver using molar mass. So we have 168.26 grams, nope, moles of AgNO3. From here, it says we have 1 mole of silver nitrate for every mole of silver metal. So we have 1 mole AgNO3 for every 1 mole Ag. Periodic table says that the molar mass of silver is 107.87. So that's 107.87 grams for every 1 mole of Ag. Moles cancels with moles. Ag cancels with Ag. That is everything. Plug it into a calculator and you get 18,122 grams of Ag. I've got 5 sig figs here, infinite sig figs here, and 5 sig figs here. So that is where I cut it off. In the next question, it says I have 42.5 grams of silver nitrate produced. And it's asking how many molecules of water are produced at the same time. So I'm going to go from grams of AgNO3 to moles, because when in doubt, go to moles. From the molar ratio, I can swap from AgNO3 to H2O because we have, once again, our equation, and these are both part of the same equation. It's a 1-to-1 ratio, so it's going to be 1/1, but for now, we're just going to put that we can get to moles of water. And for moles of water, I can go to molecules of water because we've got Avogadro's number. So when we do our final, we have 42.5 grams AgNO3. Let's do our units for everything first. For every arrow you have, you're going to have a multiplication. So we have moles of AgNO3, grams to moles of AgNO3. And then we go mole AgNO3 to moles of water. And then finally, moles of H2O to molecules of H2O. Silver nitrate is luckily given, I believe, did they not? There we go. Silver nitrate is 169.8731. I'm going to do these in a different color. I'm feeling crazy. 169.8731 for every 1 mole. Like we said, this is a 1-to-1 ratio. And then Avogadro's number is 6.022 times 10 to the 23rd, which, if you don't have memorized by now, I'm concerned, truly. So we have 3 sig figs in the first part, 7 sig figs here. This one's got infinite, and this has 4 sig figs. So we're going to go with 3, which gives us 1.51 times 10 to the 23 molecules H2O. It now asks, what is the molar concentration of nitric acid if it takes 450.0 mLs of the acid to produce 3.44 times 10 to the 24 molecules of nitrogen monoxide? This one, this sucks. I 100% believe that your professor, if it is Bonas or Bradbury, would put this on an exam. They want to challenge you and they want to see if you can do this. I'm pretty sure Lou would skip this problem. She just seems like the type to do that. I don't know anything about anyone else that is currently a 110 professor. But yeah, they would totally do that. So we're going to start this as a ratio. So this is already in milliliters of acid, so that's going to be on our bottom. And we're going to treat this like a rate problem. So this is ml of solution over 3.44 times 10 to the 24 molecules of nitrogen. And this isn't nitrogen monoxide, it's nitrogen dioxide of NO2. So I need to take the molecules of NO2, convert them to moles of NO2, because from there I can get to my acid, the HNO3 moles, and then from there, that's it. from the bottom, I just got to go from milliliters to liters. So we're going to do the top first. I got to go from 6.022 times 10 to 23 molecules of NO2 to 1 mole NO2 times our mole ratio says that we have, for every 1 mole of nitrogen dioxide, I have 2 moles of nitric acid. So when we do this, it's going to be 1 mole NO2 to 2 mole HNO3. And now we're going to do the bottom. So for every 1 milliliter, there's 10 to the negative 3 liters. Canceled out molecules here. Nitrate got canceled here. This is where I want it to be. And then milliliters canceled here. This is where I want it to be. Because if you remember, molar concentration is molarity. That's big M. That's moles over liters. So when I plug this in, I'm going to get 25.4 moles over liters of HNO3, which is the same as writing 25.4 mHNO3, which is your final answer. We are almost done, and by that I mean we have 2 more pages of math. Yay! Okay. Question 2 says we have, let me highlight it, 35.02 milliliters of 4.0 molar aluminum nitrate and 50 grams of potassium carbonate. Before we do anything else, let's balance this. So I've got a double replacement of, we got aluminum, potassium, nitrate, and carbonate. On this side, I've got 1, 2, 3, and 1. On this side, I've got aluminum. I need to rewrite them. Aluminum, potassium, nitrate, and carbonate. On this side, I've got 1 potassium, 1 nitrate, 3 carbonates, 2 aluminums. So first thing I need to do is follow this, which means I'm going to double that, getting me 2 aluminums. And now I have 6 nitrates. Following down the line, I need 2 potassiums. But I know later I'm going to have to get to 6 nitrates. So I'm just going to slap a 6 on this now, which updates this to 6 and is going to change this to 6. And then we'll figure it out when we get to carbonate. Carbonate, we've got 3 on this side, and I've got 1 on this side. I'm going to need 3 carbonates. Gonna put a 3 here. That's going to change my carbonates to 3, and it's going to change my potassiums to 6. Hey, it balanced itself out. It's almost like I know what I'm doing. Okay. And aluminum, he's just got 1. And it's asking us to fill out the solubility of these 2 because he's so nice. Okay, KNO3, she's aqueous. Aluminum carbonate, she's solid because there's no exception for her in the solubility rules. We need to figure out the limiting reactant. So we're going to take our amounts of each of our little items. So we've got those milliliters of aluminum nitrate, and we've got the grams of potassium carbonate. And we're going to convert them into moles of one of our products and see which one gives us more. If whichever one gives us less, that's our limiting reactant. So we'll start with aluminum nitrate. We have 35.02 milliliters of solution. We're going to multiply that. First, we need to get to liters because molarity is moles over liters. So we need 1 milliliter for every 10 to the negative 3 liters. Now that we're in liters, for every 1 liter of solution, there's 4.0 moles of aluminum nitrate. From there, let's pick aluminum carbonate because I just feel like it. I don't know. So for every 2 moles of aluminum nitrate, we have 1 mole of aluminum carbonate. And that is going to get us an amount. I'm actually, because it's eventually going to ask us. Oh, and it asks for the mass of precipitate later, and the precipitate is aluminum carbonate. So I just kind of like predicted what I didn't read for later. If in a secondary, like a follow-up question asks for the grams of precipitate produced, then you look for whatever was solid. That's your precipitate. This is your PPT. And since it's asking for mass, I'm just going to turn this to mass now. So for every 1 mole of Al2CO3, oh, I have just enough space to give a product, Jesus. I think it gives it to us here. Aluminum carbonate, 223.9898, beautiful. I went too far. I guess I don't have enough room. That's okay. So when calculated, our product is going to be 28.2. No, it's not. I'm looking at the wrong one. So when added together or calculated, our total comes out to 16 grams of Al2CO3. We got 2 sig figs from the molarity. So now we have our 50 grams of potassium carbonate. We got to get that into moles to follow the steps above. We're basically just doing from here on, it's the exact same. Well, just from like here on, more like. So we need to find a way to get to moles of the potassium carbonate so we can therefore continue this process. So K2CO3, that is 138.2055. Grams times, oh, not 50, it's 50.0. Every single professor will kill you if you don't have the right amount of sig figs, so fix that. In our mole ratio, it says we have 3 potassium carbonates for every aluminum carbonate. So we have 3 K2CO3 for every 1 mole of Al2CO3. 3. And we just copy paste the last part, like I said, for every 1 mole. And that gets us to 28.2 grams of aluminum carbonate. We get much less of aluminum carbonate from the aluminum nitrate solution, so that is our limiting reactant. We circle this, we label that, we write that it is the AlNO3. The maximum mass of precipitate produced, since you did the work already, you just get to write 16 grams of Al2CO3. Once again, the precipitate is whatever is solid in the reaction. Aluminum carbonate is solid, therefore it is our solid. There is that. Okay, since this is the limiting reactant, you're gonna have 0 grams left. Potassium carbonate, you started with 50 grams. However, that's not how much is going to be used. We just determined it's going to be in excess. There's going to be leftover. So to figure out how much we are going to use of it, we're going to start with our 35.02 milliliters again. And basically, this is literally going to get copied. So I'm going to start doing that. 35.02 milliliters times 1, 10 to the negative 3 liters for every 1 milliliter, times 4.0 moles of AlNO3 for every 1 liter solution, times, now here is where it gets different. We have 2 moles of aluminum nitrate for every 3 moles of potassium carbonate. So it's 2 mole AlNO3 to 3 mole K2CO3. Then we convert to grams, which we know from up here is 138.2055 grams for every 1 mole of K2CO3, which means we ended up using, we have 2 sig figs, 29 grams. To find how much is left, we have a total of 50.0 grams, and we take away those 29 we use, we get 21 grams of K2CO3. K2CO3 left over. I'm lazy. Oh, it's yield. Okay. Under the appropriate reaction conditions, Hey, it's already balanced for you. Sorry, I got distracted. We have PCl and H2O produces phosphorus acid and hydrochloric acid, according to this reaction. What is the theoretical yield in grams of phosphorus acid if 9.44 times 10 to the 23 molecules of water and 250.0 grams of phosphorus trichloride are mixed? So, step one, you need to find your limiting reactant. It doesn't say you do, but because it gives you amounts of your two reactants, you don't know which one's going to run out first, so you need to figure that out for yourself. Be independent. So we'll start with our water and phosphorus trichloride, right? Yeah. Water says we have 9.44 times 10 to the 24, yeah, molecules of water. And we've got 250.0 grams of phosphorus trichloride. First things first, we got to get to moles of our reactant. So that's for every 6.022 times 10 to the 23rd molecules of water, we get 1 mole. And then in the reaction, it says we have for every 3 moles of H2O. Does it ask? Okay, it asks for the theoretical yield of phosphorus acid. So we need to convert this to phosphorus acid. So it's for every 3 moles of H2O, we have 1 mole of phosphoric acid. And then from there, go to grams. That is 82.01. For this one, we literally do the same thing, but we go from, instead of going from molecules to moles, we're going from grams to moles. So for every 1 mole, and that is 137.32. And then for every 1 mole of phosphoric acid, we have 1 mole of PCl3, phosphorus trichloride, and then 82.01 grams for every 1 mole of phosphoric acid. Okay, for part A, you get with sig figs. So in the first part, I've got 3 sig figs, 4 sig figs, ratios have infinite, and this has 4. So we end up with 3 sig figs to get 428 grams of phosphoric acid. And then the bottom one, we have 4 sig figs here, 5 sig figs there, infinite and 4. Lowest amount is 4, so we're gonna have 4, getting us 149.3 grams of H3PO4. Smallest amount is this one, meaning this is our limiting reactant and we have water in excess, which makes sense. So the theoretical yield in grams is 149.3 grams of H3PO4. For the next one, it says if the percent yield is 76.2%, what is the actual yield? we're gonna take this and turn it into a conversion factor. So a percent is out of 100, right? If you got a 76.2%, then that's out of 100%. So we say for every 76.2 grams actual, it's 100 grams theoretical. We're gonna start, because this is our limiting reactant, we're gonna take this and just rewrite it. It's to the point where I'm literally just going to do that. Make my life easy. From here, we need to use our mole ratio with the hydrochloric acid. So, for every 1 mole of phosphorus trichloride, we have 3 moles of HCl up here. We've got an invisible 1 here, and we've got a real 3 here, represented here. From here, we go to grams of hydrochloric acid, which is given right here, 36.46. So that is our full equation, getting us 151 point. Actually, before I do that, we've got 4 sig figs, 5 sig figs, infinite, and 4 sig figs again, and then 3 sig figs here, giving us, originally it's 151.7 grams. However, we only have 3 sig figs, so this is gonna round up, getting us 152 point grams HCl is our answer. Yay, we did it!